Good afternoon, everyone. Welcome back. And if you have any questions during this session, please type in the Q&A box, and we will find the appropriate time for Professor Senthil to address. And this afternoon, we are very happy to have Professor Senthil Todadri from MIT to give 2 lectures. And Professor Senthil is a renowned theorist who have broad interest over many different interacting electron systems. And many of you probably know him by his pioneering work in quantum spin liquids. And however, today he's going to tell us about a more recent and very popular platform of Moiré Graphene systems. So let's welcome Professor Senthil to give his talk.
Hey, thank you. Yeah, mute myself. Oops. So can you see my screen?
We cannot see the video. We can't see the slides. Oh, we can see the video.
Yeah. So everything good? You can hear me and everything?
Yeah, everything's good.
All right, very good. So let me get started. So thank you, Xiaoming, for the invitation to speak in the school and for all the organizers of the school for putting this together. It's wonderful that we're all able to connect through Zoom. Yeah, so the work that I'm going to, the topic that I'm going to introduce to you today is Moiré Graphene materials. And I'm going to be talking about topology and correlations in Moiré Graphene materials. So before I get started, just out of curiosity, I wanted to know what fraction of the audience listening in are experimentalists and what fractions are theorists. So Xiaoming is running a poll. So if you can answer that poll, it'd be wonderful. Thank you. All right. So much of what I know about this topic it comes from various collaborations that I've been involved in. So in the top row of various students that I've worked with in the last couple of years, Yohei Zhang. Much of what I'm telling you actually was work done by Yohei Zhang. He was a graduate student with me at MIT, and he moved to Harvard last year as a postdoc. And Liu Jin Zhu, who was also a grad student with me, and he moved to Perimeter as a postdoc last year. And my current students, Dan Mao, Jihoon Dong, and Jenny Crawford. And postdocs, Adrian Poe, from whom I learned a tremendous amount about band theory that I didn't know before. And Cecile Reppelin, who did some wonderful ED calculations, and Debanjan Chaudhry, with whom I had a nice collaboration on transport and twisted bilayer graphene. And most importantly, actually, just as importantly, my experimentalist colleagues, in particular, Pablo Herrero, whose experiments kickstarted this field, and also had nice collaborations with Feng Bong at Berkeley and David Goldhaber-Gordon at Stanford, and their students and postdocs, and my longtime friend and collaborator, Ashwin Vishwanath, who's at Harvard. Okay.
Sorry, before we get started, the poll result is coming in, and we have 95% people already voted. It seems to have 53% of people being experimentalist, and 47% is theorist.
Wonderful, thank you very much. So given that there's a slight majority of experimentalists, if I'm a theorist, so if the talk gets theory heavy at any stage, please do feel free to stop me and question me. And likewise for theorists as well. So if you have questions in the middle that you'd like to get clarified, you're more than welcome to stop me in the middle. Or if you prefer, you can wait till the end as well and type it into the Q&A or something. All right, so this topic has gotten a lot of attention in the last 2 years. So I presume all of you have heard of a little bit at least of what's going on. So Moiré patterns and twisted bilayer graphene. So if you take 2 layers of graphene that are twisted relative to each other, take 1 layer of graphene, put it on top of another layer of graphene with a slight twist, then the interference between these 2 crystal patterns leads to this Moiré structure, which on the face of it forms a triangular lattice, right? And with a period that is much bigger than the period of the individual graphene lattices. Okay. Now, what we're interested in is the electronic properties of this structure, and this superlattice that's created by the Moiré potential strongly reconstructs the electronic bands, and if the twist angle is small, the Dirac cones of each of the 2 graphene layers couple strongly to each other, and you get a modified electronic structure. So I'm going to spend a few minutes sort of talking about the old history of this subject. This will be very quick, and then we'll launch into the talk proper. Okay. So the old history, the prehistory, starts more than 10 years back with people, the theorists who started thinking about this kind of system. And there were some very important ideas that were introduced in that early work. And the first is that small twist angles in the structure, there is a well-defined universal band structure that forms that's independent of most details of the Moiré lattice. In particular, you might worry that whether or not the 2 lattices that you're rotating relative to each other, whether they are commensurate with each other or incommensurate. So it turns out that at small twist angles, those kinds of details do not matter. And momentum in the combined Moiré structure is well defined, and you can talk about bands and things of that sort. Now, these bands, they live inside a hexagonal mini Brillouin zone. So this mini Brillouin zone corresponds to the long period of the real space Moiré lattice. And so these Brillouin zones, red and blue, are the Brillouin zones of each of the 2 graphene layers. You form these tiny Brillouin zones at the 2 corners of each of these. And all the action happens inside these tiny Brillouin zones, these so-called mini Brillouin zones. So this idea that the bands are well-defined in this twisted bilayer graphene at small twist angles has been benchmarked against a variety of explicit calculations. For instance, you could take a commensurate structure at some small twist angle and just do a standard tight binding band calculation and see what that looks like and compare it with the continuum theory that was developed in these papers, which makes no reference to whether or not the structure is commensurate or incommensurate. Okay, and the answer basically is captured correctly by this continuum theory. Now, as part of the same body of work, what people realized was that these reconstructed bands become very flat if you tune the twist angle close to some magic values. Okay, and this was the paper that did this in a most microscopically accurate manner was that by Bitzlitzer and MacDonald nearly 10 years back. And what they found is that the first magic angle is at about 1.1 degrees. And they produced a band structure at this magic angle. So I've shown here a reproduction in some modern calculations and found in some subset of these papers. And you see the bands plotted inside this mini Brillouin zone as a function of momentum. And on this scale, this vertical axis is 200 millielectron volts. On this scale, you barely resolve the width of these bands right in the middle. So these are the narrow, flat bands. That's where all the interesting things are going to happen. And if I blow up this tiny region, I get this plot on the right, where you see that the width of this plot goes from 4 millielectron volts to minus 4 millielectron volts. So on this big scale on the left, you hardly resolve it. And you see that indeed there's some dispersion, there's some band structure, so it's not exactly flat, but the bandwidth is only about 8 millielectron volts or so, much narrower than the bandwidth of microscopic graphene, of ordinary monolayer graphene, which is on an electron volt scale. Okay. Now, Bitzitzer MacDonald also realized that this narrow bandwidth means that there may be interesting correlation effects in this system. So the estimated bandwidth was on the scale of 10 millielectron volts. If you estimate the Coulomb interaction, the Coulomb interaction U is also comparable to the bandwidth. Okay, so given that the Coulomb interaction is order the bandwidth, you might imagine that the electron-electron interactions start playing a role in determining some of the physics. But it wasn't clear what exactly would happen, and this just remained sort of a theorist's dream. So the recent excitement started 2.5 years back with experiments done by my colleague, Pablo Herrero at MIT. And quite dramatically, his group discovered that if you take nearly magic angle twisted bilayer graphene, then all kinds of correlated electron physics is apparent. So this is a plot of the conductivity of one of the devices they made, plotted as a function of the carrier density. So n equals 0 means it's charge neutrality. Now you see the carrier density, the scale for the carrier density is 10 to the 12 per centimeter squared. So it's an extremely low density system. So the first thing to pay attention to is what happens as you tune. So the carrier density is tuned using gate voltages. So if you hold dope away from neutrality, you get to this regime where the conductance has gone to 0. And likewise, if you electron dope it, you go here, then you get to a regime where the conductance is once again gone to 0. Okay. Now, so these we understand or correspond to fillings at which the system is a band insulator. So this Moiré potential reconstructs the lattice, forms bands within this mini Brillouin zone. And this filling corresponds to a filling in which some sort of bands are fully occupied and the flat bands, which is this region, are fully empty. And likewise, this region corresponds to a situation in which you've occupied all the flat bands, but not any of the higher energy bands. Okay, and these insulators have big band gaps. The transport measurement, by measuring the temperature dependence of the conductance, you can extract out an estimate of the gap. And the gap turns out to be big. It's about 35 millielectron volts. Okay. So these two endpoints are band insulators. Okay. So everywhere in the middle, you have a situation in which these flat bands are partially filled. And the most interesting observation that was made was that right at the midway point between neutrality and this fully empty insulator, there's another dip in the conductance, and you get another insulator. And likewise, exactly midway on the electron dope side, you again get an insulator. Okay, so these are insulators at partial band filling, and presumably then the thinking was that these must be driven by electron-electron interactions, because within band theory, you would get a metal at these fillings. So that was exciting, that in graphene, that by doing this trick of flattening the bands by going to magic angle twisted bilayer, that you're able to see a correlation-driven insulator in the middle of a band. Now, because this system can be easily tuned with gate voltages, Pablo's group, Pablo and his students, they managed to dope away from this correlated insulator. So they called it a Mott insulator in their original paper. They'll get back to this. But this insulator at partial band filling, when you dope slightly away, they discovered that you get a superconductor. Okay, so in this original data, the superconductivity is on the the maximum TC is about 1 Kelvin. So these days, people make devices in which the TC is on the order of maybe up to 3 Kelvin or so. Okay, so you see a correlated insulator, and you see superconductivity in the vicinity of that correlated insulator. Okay, so this was interesting. It was a very unusual platform to see such phenomena, and these experiments were quickly reproduced by other groups. So here's data from the group of Andrea Young and Corey Dean, or rather, they are combined groups. So there's various things in this plot, but overall, the overall message is that yes, indeed, the phenomena that were reported earlier, they saw it too, and they saw other features, like, for instance, superconductivity on the electron dope side of neutrality. And as the field has progressed, people have developed various other, more elaborate ways of controlling these systems. So in this paper, which was the second experimental paper in this field, they introduced dual-gated samples. And the presence of dual gates means that they could control, they could apply a perpendicular electric field to this device. And that's the knob that you can tune to change the electronic properties. They also use pressure as a vehicle to tune the electronic properties. So there's all kinds of things that were done. So in this plot, for instance, you see that at midway between the neutrality and the fully filled insulator, on the electric hole dope side, at zero displacement field, you do not see, you see a metallic behavior. But as you increase the displacement field, you enter a regime where you get a correlated insulator. While on the electron dope side, at any displacement field, that's a correlated insulator. Okay, so this was wonderful. Wonderful confirmation, wonderful progress from this this paper, and the field evolved quite a bit more, was pushed forward by this third paper that came from the group of Dima Efetov. So he made twisted bilayer graphene devices and then had some way of controlling a type of inhomogeneity that people knew existed in some form or the other in these devices, which is an inhomogeneity in the twist angle, where it varies slightly from one location to the other location. So Efetov's group thought they had a way of controlling that a little bit, and then they found an even broader range of dopings in which the system is superconducting. And these superconducting regions are punctuated by regions of correlated insulator. Right? So you see these resistance peaks that correspond to the correlated insulator and flanked by superconductors in a wide range of doping. And there's been a tremendous amount of further development since, various kinds of other experiments, some of which I might talk about. But I want to talk about other developments in this Moiré graphene, which are equally interesting. So it turns out that twisted bilayer graphene is just one member of an entire class of materials of what we may broadly call Moiré graphene materials. For instance, instead of twisting one layer of graphene relative to another layer of graphene, you could take n-layer graphene and twist it relative to another n layers of graphene. So the example, the classic one, the one that Pablo initially worked on, had n equals m equals 1. But there are other systems that people have studied since, which also look fascinating. A popular system is where n equals m equals 2, twisted double bilayer. So you take ordinary Bernal stack bilayer graphene, you take another ordinary Bernal stack bilayer graphene, and you twist one relative to the other. And beautiful experiments on this system have in fact been done by our host, Xiaoming Liu. that I'll mention as we go along. So that's one route. Another route to making interesting Moiré graphene structures. Now, yet another route is to not do any twisting at all, but rather to take N-layer graphene and align it with a hexagonal boron nitride substrate. Now, it turns out that, and many of you probably know this, HBN is a very popular substrate for graphene experiments, but there's a slight lattice mismatch between graphene and boron nitride, and the slight lattice mismatch leads to a large period Moiré pattern. And this Moiré pattern, again, reconstructs electronic bands and does all kinds of interesting things. So this was demonstrated first very nicely in some beautiful experiments by Feng Wang on ABC stacked tri-layer graphene, nearly aligned with hexagonal boron nitride. And he showed that you get correlated electron physics in that system as well. Okay, so there's many kinds of amazing things that have been discovered in the last 2.5 years in this field. So in the original twisted bilayer graphene, the experiments that I already mentioned show the correlated insulator and superconductivity. If I have time, I might show a slide on some weird metallic transport that has been observed. Now, if you take this ordinary twisted bilayer graphene and you further align it with a hexagonal boron nitride substrate, so you have magic angle twisted bilayer graphene, and then you take one of these two graphene layers and you align it with the boron nitride substrate. So that system has been studied, and it does something very interesting. It shows ferromagnetism, okay? And it also shows an anomalous Hall effect, which it turns out, at least in some of the experiments, is a quantum anomalous Hall effect. They're a very nice example of a 2D material showing a quantum anomalous Hall effect. The ABC tri-layer graphene system aligned on HBN. So Feng Wang's group, sometimes in collaboration with Golub Gordon, showed that you get gate tunable Mott insulators. So you can tune in and out to the correlated insulator with a gate. You also get churn insulators in this system, which again you can tune with a gate. You get ferromagnetism. There is even some signatures of superconductivity. Now, in twisted double bilayer graphene, there are experiments by Philip Kim, by Pablo, and by a group in China. Chao Meng was working in Philip Kim's group when he did these beautiful experiments. There's evidence for spin polarized correlated insulators. And there's some suggestive evidence, perhaps, that there may even be superconductivity in this system. Very recently, people have studied bilayer graphene, twisted relative to monolayer graphene, and again found ferromagnetism and a possibly quantized anomalous Hall effect. So, there's a rich range of phenomena that have been found, and it's amazing to step back and think that all this is happening in just, atomically thin layers of carbon, right? There's no, transition metal ions, none, or rare earths, none of those objects in the periodic table. It's just carbon doing everything, right? Which is kind of cool. Okay. So what I wanted to do, so there's a large number of experiments, and there's a very rich phenomenology in each one of these systems. But rather, because this is a school, what I thought may be useful to do is to give you some perspective on where this stands in the big landscape of quantum materials physics, and then talk about what we've learned about what I'm a theorist, right? So what we've learned theoretically about what the fundamental questions are in modeling this system. Okay, so that's what I'm going to focus on in these lectures. So questions that you could ask, or how should you think about the phenomena that have already been seen, the correlated insulator, the superconductor, maybe the ferromagnetism, things of that sort. From a theoretical point of view, you could ask, if you want to build a model of these systems, what are the important ingredients that you have to keep? Now, obviously, the superconductivity near the correlated insulator immediately calls for an analogy to cuprates and other correlated solids. So is this a replay of the same story, but perhaps with a different lattice and with more degrees of freedom, or is it something different? Okay, so these are some of the questions that one could want to answer, some of the high-level, broad questions. Okay.
Professor Senthil just interrupts. Someone raised their hand with a question, so I'm going to allow him to ask his question verbally.
Sure.
Joshua, you can speak.
Can you hear me?
Yeah.
Okay. I just had a quick question. You mentioned before that there's a metallic phase cracked in a Moiré graphene material. So wouldn't this be a marginal Fermi liquid away from charge neutrality point, or isn't this just a regular Fermi liquid?
We don't know.
No. Okay.
At the lowest temperatures, there's no evidence to assume. No, that's not right. That's the kind of question that's best to keep an open mind on. It's probably a Fermi liquid. That's my guess.
Okay.
But yeah. Let me just leave it at that.
Okay. Thank you.
One of my last slides is on transport in the normal state. So if I get to that, and if you haven't seen it already, you'll see for yourself what the resistivity looks like.
Okay, thank you.
Sure. All right, so I'm going to start at a very basic place. So my apologies if this is a bit too elementary to some of you. So I'm going to give a very brief primer on correlated electron solids. Okay. I think it will be useful to do that. Yeah. So in thinking about strongly interacting electrons in solids, so what we usually mean is that a weak coupling perturbative treatment of Coulomb interaction fails. That means that a simple Hartree-Fock-like approximation is probably not enough to capture the physics. That's the phenomenon of strongly correlated electrons. And there's many interesting phenomena that result in a strongly correlated material. And a simple example is a Mott insulator that I know that everyone has heard of because you're at least graduate students in condensed matter physics. But let me quickly remind you that it's an insulator that occurs due to the jamming effect of Coulomb repulsion. The Coulomb cost of two electrons occupying the same atomic orbital, if that dominates at commensurate filling over the band energy, then the electrons can't move and you get an insulator. So this is a situation in which you have an odd number of electrons per unit cell and band theory predicts a metal. But that for very simple reasons, instead, you get an insulator. Okay. Now, and this also everybody knows, an important corollary of having a Mott insulator is that you get magnetism. This was addressed in the 1950s by Phil Anderson and was part of what got him his physics Nobel Prize, one amongst many things that could have gotten him his Nobel Prize. If you take the electron hopping on the lattice in perturbation theory, now remember the electron is just following the on-site Coulomb repulsion. So if you perturb in the electron kinetic energy, then the anti-align spin configuration allows electrons to make virtual hops to neighboring sites. So this favors antiferromagnetic interactions of neighboring spins. So naturally, the spins of the electrons try to form an antiferromagnet. And indeed, antiferromagnetism is the most common form of magnetism in insulators. There is, years later, there was a very delicate mechanism that was worked out, which enables, in some cases, for ferromagnetism to arise in insulators. But it's rare and it gives very weak magnetism. So there's very few ferromagnetic insulators that are known. Most magnetic insulators are antiferromagnetic insulators. Now, the Mott insulator, it's most simply understood from a real space point of view. Just think of the electrons as particles. Now, this should be contrasted with a metal, which we understand from a momentum space point of view in terms of filling a Fermi surface. So, which means we think metals are simply understood by thinking of electrons as waves. And Mott insulator is simply understood by thinking of electrons as particles. So if you have a system that's on the verge of a transition between a metal and a Mott insulator, then there's confusion, and neither the particle nor wave points of view is necessarily superior, and all kinds of weird things can happen. And the most striking example is high temperature superconductivity. Maybe not the most, but certainly one of the most. Now, hopefully everybody has seen the phase diagram of high TC materials before. 10 years back, it was safe to assume that you'd seen it. Every student had seen, a condensed matter student had seen it. So often enough to be bored of it. I realized I can no longer make that assumption. But the basic point is that these materials start off as Mott insulators, and then you remove electrons by changing the chemical composition, and something happens and you get a superconductor. Right? So superconductivity occurs in the vicinity of the Mott insulator in the high temperature superconductors. Now, there's other examples. So this is an interesting example. These are in quasi two-dimensional organic salts. The abbreviation is kappa ET2X. So X is some chemical unit which separates layers of ET. So the electronically active layers are these ET layers. So this system, at the end of the day, so people have modeled this system and some try to make a reasonably detailed model. And at the end of the day, what happens is that these ET layers, each ET molecule, rather a dimer of molecules, has one free electron left in it. And these dimers form a triangular lattice. And the model of the system is electrons hopping on an anisotropic triangular lattice. Okay, and these typically start off as Mott insulators. Now, these organics can be easily tuned with pressure. So when you tune pressure, in one example, there's one example of a class of examples within this family of materials. You go from an antiferromagnetic Mott insulator to a Mott transition to a metal which at low temperatures is a superconductor. Okay, so this again is an example of superconductivity in the vicinity of the Mott transition. Okay, now there's another entertaining example. This is in buckyballs, C60. You make a compound like cesium-3 C60. It forms an FCC structure, and at ambient pressure, this again turns out to be a Mott insulator, and it's a frustrated Mott insulator. It has a Curie temperature of more than about 35 Kelvin or so, but it doesn't order down to very, very low temperatures. Now, if you apply pressure to this, again, there's a Mott transition, and you get a reasonably high temperature superconductor. It's like 30-something Kelvin TC, right? So, the point is that there's many, many examples by now, or in diverse varieties of quantum materials, where you get superconductivity in the vicinity of a Mott insulator. Okay, so the natural question to ask is: Moiré Graphene another example of the same story or not? Okay, so given a phase diagram like this, it's very tempting to say that it's just really another instance of a phenomenon that is at least familiar, even if not completely understood. So let's now think about how typically in textbooks we model a correlated solid, right? So the first thing to do is to think about the band structure. Now there'll always be a bunch of remote bands, filled bands that are deep below the chemical potential. We don't care about these. There'll also be a set of empty bands that are far away from the chemical potential. We don't care about those as well. What we care about are bands that are near the chemical potential, right? And so long as the typical Coulomb interaction strength is much smaller than the gap between the active and remote bands, right? What the right way to model this solid is to project the interaction to within the active band to get an effective model in block space, right? So the Hamiltonian will look something like this. There is some dispersion, a single particle dispersion, and then there's some Coulomb interaction. There's some interaction which in the block basis has some such form, right? Here I've suppressed, spin and perhaps orbital indices if they exist and so on. And in principle, to a Hamiltonian of this sort, you need to couple the electrons to phonons, you had to couple it to impurities, and so on and so forth. So that's solid state physics 101. Now, we often model correlated electron systems through a lattice effector model, for instance, a Hubbard model. So the way to go from this block basis Hamiltonian to something like a Hubbard model is to transform from the momentum basis to the Moire basis. So associated with block functions, psi k of r in a band, you do this lattice Fourier transform, you get these Moire functions, which are associated with lattice sites r, and there are some functions of little r, which are centered at some lattice sites capital R. So this is a change of basis. And for ordinary bands, and I'll qualify the word ordinary in a minute, it's possible to construct well-localized Moire functions that transform nicely under all microscopic symmetries. And then if you go from this, rewrite the Hamiltonian, rather than in the block basis, you rewrite it in the Moire basis, you get a tight binding model plus interactions, which is then your effective interacting lattice model. This is the way to justify, for instance, the Hubbard model description microscopically in a correlated electron system, and so on and so forth. Okay.
Thank you. Chun-Li asked, what is the justification of not caring about remote bands?
Oh, the justification is this criterion: if the interaction strength is much smaller than the gap between active and remote bands, right? So the matrix elements that mix states here with states there of the interaction, the one particle Hamiltonian doesn't mix these states, right? It's obtained by diagonalizing one particle Hamiltonian. The interaction doesn't couple these states together strongly, right? So then you can forget about these bands and just project the interaction into this. Is that good?
Chun-Li, if you have further question, you can raise your hand. No?
All right. Okay. So, so this is the standard strategy to produce a lattice model. Now, let's ask about Moiré Graphene materials. As we'll see, there are some Moiré Graphene systems that fit the standard framework, but the vast majority do not. And the reason is the second theme of my lectures, which is that the band structure of most of these Moiré Graphene materials have non-trivial band topology, and the band topology prevents passage to a nice Moire basis. So as to the question of whether Moiré Graphene is just the next term in this series of materials that started with the cuprates on super pretty near a Mott insulator, at least theoretically, we see that the eventual understanding of these systems cannot be within the same framework that's used to describe other typical correlated materials, right? Okay, so the next primer I want to give is on topological band theory. So unlike, say, cuprate superconductivity, this has been the hot topic in condensed matter physics in the last 15 years. So I'm going to be very brief and somewhat fast. Again, hopefully this is familiar. So let's start with some basics of band theory. Right? So we have electrons in a d-dimensional periodic crystal, then momentum space is a torus. Think about 2 dimensions, that's all we need. In 2 dimensions, the below zone is a torus. So the real space looks like a lattice, the momentum space looks like this. And there are quantum mechanics, there's block states nk for each band n with momentum k, and there's some energy dispersion. Now, a crucial part of the story is that there are Berry phases and momentum space. An electron moves around k space in a loop, and its quantum wave function can return with a Berry phase. And we think of the Berry phase as a flux of a momentum space magnetic field, Bk, often called Berry curvature. That's determined by these wave functions through a precise formula. And the momentum space magnetic field affects the semi-classical equations of motion in just the same way as a real space magnetic field affects the semi-classical equation of motion, it affects the d or dt by having the standard term plus another term that depends on k dot cross b. So the standard term is called the normal velocity, and this new additional term is called the anomalous velocity. And given that dk dt is determined by the external electric field, you see that this anomalous velocity is proportional, is perpendicular to the external applied field. It's a transverse velocity. Now, an interesting case is that of Chern bands in 2 dimensions, discussed first by Thouless and Haldane in the 1980s, which was part of their Nobel Prize. So in 2D, for an isolated band, the total momentum space magnetic flux is 2 pi times an integer. And that integer is what's called the Chern number. This Chern number can be thought of as counting the total number of momentum space magnetic monopoles confined by the momentum space torus. And because it's an integer, it's a topological invariant, and bands with different Cn are topologically distinct. Now, a Chern insulator is a material with a filled Chern band, and the anomalous velocity, if you integrate it over the entire below zone, you'll see that it leads to a net current that's perpendicular to an applied electric field. In other words, there's a Hall conductivity, which is quantized to be the Chern number times c squared over h. So a Chern insulator has a quantized Hall conductivity. And of course, the most famous example of this is the integer quantum Hall effect. And we know that you get chiral edge states and so on and so forth. And of course, a Chern insulator requires absence of time reversal symmetry. Okay, now the part of the story that's crucial for what I'm going to say is that if you have a Chern band, it's not possible to construct well-localized one-year functions to go to a tight binding model. So this was proven as a formal theorem in 2007 by Bruder and Mazzari and others. But the intuition is very simple. It is that since the Chern band encloses the magnetic monopole in K space, this means that the phase of the block wave function cannot be globally well defined. The best you can do is to define it in patches and momentum space. And where patches overlap, you define a momentum space gauge transformation to sort together these different patches. So the integrand in the K-space integral that defines the one-year function is not smooth. And so there's no well-localized one-year functions. Okay. Again, this may be familiar. So corollary of this result is that if I have a partially filled Chern band, not a Chern insulator, but a partially filled Chern band, which also happens to be strongly correlated, then there's no way that I can describe it, but simply by a lattice effective model. I can't write on a Hubbard model or any such thing. For such a system, the best that I can do is to introduce some extraneous, unwanted degrees of freedom, some auxiliary bands with opposite Chern number, right? Thing that you may know about model, which has 2 bands, one equal opposite Chern number, separate G space, right? But just focus on the active partially filled Chern band. There's no way I can build an effective lattice model, and I had to describe the system in a different way. Now let's generalize this to symmetry protected band topology, for instance, to topological insulators. I won't actually need to think about standard topological insulators, but instead, let me use a simple example to see how it works when the band topology is symmetry protected. And this is an example that will actually play a role in these systems, the Moiré Graphene systems. So let's consider a system with 2 active bands with equal and opposite Chern number, right? A 2-band system. There's 2 active bands, and all these are, the pink is all remote bands. And let's assume that even in the presence of interactions, the number of electrons within either band is conserved. So interactions only couple the electrons in these 2 bands through Coulomb repulsion, but not through electron hybridization. So then there's a global U1 cross U1 symmetry corresponding to particle number conservation separately in either of these 2 bands. And in this system, the band topology is protected by this U1 cross U1 symmetry. Okay, the net Chern number is 0. The sum of the Chern numbers of both bands is 0. So in principle, you can construct localized Moire functions, but these localized Moire functions will be mixtures of states of the two bands. They'll be hybridized between the two bands, which means that the action of the global U1 cross U1 symmetry will be complicated. In fact, it cannot be a local action where a single Moire orbital just goes into itself under action of the symmetry. So this is an interesting situation where you can construct Moire functions, but at the price that you don't know how symmetry acts, how the global symmetry that exists in the system acts. So this story is repeated in all modern examples of topological insulators, and this was discussed many years back by Vanderbilt and his student Solian now for transversal symmetric topological insulators. But it's the same story for every other symmetry protected topological insulator. So if we want to make a lattice model of this system, again without adding extra bands, we are playing a very dangerous game. Every theorist that's listening in knows that if you work in a representation of your system in which some symmetry is not manifest, you're playing with fire, right? You could easily make mistakes once you start making approximations, and you have no way of knowing whether you're making a mistake or not. So basically, one should avoid working in a formulation where the symmetry action is not at all, it becomes very, very complicated and it's hard to keep track of. Okay. All right. Now, there's one example of that's very well known in condensed matter physics of strong correlations in a topological flat band. It's a very special topological flat band, and that's a single Landau level. Okay. A single Landau level is a special case of a Chern band. It's exactly flat. There's no energy dispersion. And it also has exactly flat Berry curvature and other related properties. Okay. So in this special case, we know both experimentally and theoretically exactly what happens. We get the beautiful phenomena of the quantum Hall effect, the fractional quantum Hall effect, the composite Fermi liquids, and all kinds of wonderful things. And we know that we do not understand these phenomena in terms of lattice tight binding models, but rather we use completely different ways of thinking in quantum Hall physics. We use wave functions, we use effective field theories, so on and so forth. Okay. But so quantum Hall is a good example because we understand it. But away from the special limit, how should we deal with strong correlations away from the special Landau level limit of a Chern band? For instance, if the Berry curvature is not uniform, or the Chern band has a dispersion, or for other topological bands, for instance, the symmetry protected topological band, is largely an open question in many body physics. It's almost not understood. It's not understood at any level of detail. And amazingly, as we'll see, this is precisely the situation that's presented to us by many Moire materials. So in the vast landscape of quantum materials, Moire materials sort of have their own niche. They don't fit in nicely with anything else that we are familiar with and understand in the past. So that's, in a sense, the central thesis that I'm going to describe in these lectures. I took this part just to get to this punchline. So now let's launch into it. Okay. Okay. So earlier on in the talk, I said that there's all these amazing things that have been found in these Moiré Graphene systems. So let's ask about how. So rather than focusing on any single one of these systems, since an interesting phenomenon in almost all of these systems, I want to try to keep the discussion somewhat general. So let's ask about how we might model these diverse systems. So as always in condensed matter physics, the microscopic model will have a band dispersion and have some interactions. Okay, and the first thing we should try to do is to try to understand the symmetries of the problem, both the exact symmetries and the nearly and the symmetries that are extremely good if not exact. Okay. So first, let me describe some features of the band structure. So we have a bunch of active, nearly flat bands that are separated from these remote bands. Now, each one of these active flat bands, if you remember the structure, electronic structure of graphene, there are two valleys in graphene corresponding to the two corners of the hexagonal below zone. Now, corresponding to each one of those two corners, there's a separate valley that's inherited by all of these Moiré structures. And the active bands near each of these two microscopic valleys of the underlying graphene are disconnected from each other, right? So the Moiré lattice spacing is so much bigger than the graphene lattice spacing that the momentum associated with the size of this mini below zone is small compared to the size of the big below zone, and therefore compared to the separation between the two valleys. Okay, so we should think of the system as two independent valley degrees of freedom, which more or less acts as an internal degree of freedom, just like spin is an internal degree of freedom. Okay. Now, furthermore,
we have 10 minutes.
Have 10 minutes? All right, very good. I'll keep going and tell me to stop when I should stop, and I'll then pick up in the second lecture. So in many of these Moiré materials, within each valley, we can isolate the valence band energetically from the conduction band. So this is true in many of these Moiré materials, but not in all. And in particular, in the original twisted bilayer graphene, for each valley, the conduction and valence bands, the conduction band and the valence band, they're connected to each other through Dirac points, which occur at the corners of these mini below zone. So let's talk about the symmetries of the band structure. Now, one thing you may worry about is that these systems have very little symmetry, strictly speaking. So the obvious symmetries are charge conservation and time reversal. To the extent that spin orbit can be ignored, there's spin conservation as well. And so these are the obvious symmetries, but it turns out there's a large number of excellent symmetries of twisted bilayer graphene at small twist angles, which is what we're interested in. First, there's Moiré translation symmetry. Even though there's not an exact microscopic symmetry, it turns out to be an excellent symmetry as far as electronic physics is concerned. That's what I said right in the beginning slides. Momentum is a well-defined quantum number at low twist angles. There's also a C6 Moiré lattice rotation, which is a good symmetry at small twist angles. Now, the Dirac points of twisted bilayer graphene within each valley are protected by a combination of these symmetries. They're protected by a C2T symmetry. And some of you who know graphene, ordinary monolayer graphene, will know that it's C2T is also the symmetry that protects the Dirac band touchings of monolayer graphene. So now in twisted bilayer graphene, if somehow you break C2T symmetry, then generically the Dirac points will be gapped out. Now, experimentally, a way to break C2T symmetry is to take twisted bilayer graphene and align it to a boron nitride substrate. Now, since boron nitride breaks C2, the alignment with boron nitride leads to effective Hamiltonian breaks the C2T symmetry. And then theoretically, you expect that charge neutrality becomes insulating. And that's basically consistent with experiments that have been done on this system. Okay, so that's about band structure. Now let's talk about the many body Hamiltonian. Now the two Moiré below zones near each graphene valley are disconnected. This means that the separate conservation of charge and the spin of electrons in each valley. So the continuous global symmetry is what theorists like to call U2 times U2. U2 is, roughly speaking, it's U1 crosses U2. U1 corresponds to the charge and there's U2 to the spin. And this is there for each valley separately. And this global symmetry is broken weakly by an inter-valley Hund's interaction, which conserves only the total spin of the electrons, but locks the spins of electrons to the two valleys together. Now, I should emphasize that the dispersion in the opposite valleys are distinct. They're related by time reversal, but they're really distinct dispersions. So at the microscopic level, there is no SU4 spin valley symmetry. Again, those of you who work on graphene, ordinary graphene, may know about SU4 spin valley symmetry that plays a role in some of the properties. But that is broken explicitly in the system already at the level of the band structure. Rather, the symmetry that you have is this as an approximate symmetry, and this as the even better symmetry. So can we build an effective lattice model for this system? So as I already discussed, if you can one-year represent, then you can add interactions to get a Hubbard type model. But you can't do that if the bands have non-trivial topology. Now, it turns out, so in twisted barrier graphene, it turns out that the bands are indeed topological in a very subtle sense. And the sense in which they are topological, so let me sort of sketch what the essence of what's going on here. Later on, if there's time, I'll give a slightly more detailed description. So the Dirac points within each valley have the same chirality, meaning the phase of the electron wave function winds around in the same sense as you go around the Dirac points, either of the two Dirac points within a single valley. This should be contrasted with Dirac points in conventional monolayer graphene, where there's a plot of the Dirac of the direction of the effective magnetic field on the Dirac spinor. So this winds around in opposite senses in standard monolayer graphene for the two Dirac points. In contrast, here the chirality is the same for the two Dirac points. So this feature is connected to a subtle form of symmetry protected band topology known as fragile band topology. This is a notion that has gotten some attention in the last 2 or 3 years, thanks to work by Adrian Poe, Ashwin Vishnath, Andrei Bernoweg, and their collaborators. It turns out that the active bands or twisted barrier graphene have that kind of band topology. Now, the opposite valleys, since they're related by time reversal, have opposite chirality. So this is a situation where there's an obstruction to fully symmetric one-year states. Okay, so this situation is a bit subtle, it's a bit complicated. Now, if you look at many other Moiré graphene systems, they have band topology, but it's a much more familiar and simple form of band topology. So maybe I should just describe this slide, and maybe that is a good place to stop. So let me just go through the slide. So what happens in many other Moiré graphene systems is that the flat bands of the two valleys have equal and opposite Chern number C. So this is basically the example of symmetry protected band topology that I described a few slides back. So a good example is ABC trilayer graphene aligned with boron nitride. Now, it turns out that for one sign of a perpendicular displacement field, the bands in this system have non-trivial Chern number of plus minus 3 at the non-interacting level. So one valley, the band in one valley has Chern number 3, the band in another valley twisted by alignment one. So to that, twisted double bilayer, the conduction band has Chern number plus minus 2. And in all these cases, there's clearly an obstruction to writing one-year functions that preserve the value U1 symmetry. Okay. So essentially, in all these systems, we are confronted with a situation in which it doesn't make sense to write down a lattice Hubbard type model and use that as a non-dangerous guide to the physics, and we have to do something else, right? So, Xiaoming, is this a good time to stop, or do I have a few more minutes?
Yeah, let's maybe stop here since we exactly 1 hour. We'll take questions. Type your question in the Q&A box. If you want to ask your question vocally, you can raise your hand after typing your questions. So let's go through the questions raised during the talk. First, how did they estimate the Coulomb interaction? I think this referred to the beginning of the talk.
Yeah. So estimate so you just take the size of the and you
sorry,
just do
since your voice is a bit breaking up, can you repeat that?
Oh, you just take the size of the Moiré spot and you take E squared divided by the Coulomb charging energy of a Moiré spot, right? That's the estimate of the Coulomb energy, right? So there's a few nanometers. So you do E squared over the few nanometer length scale divided by the dielectric constant, and that's it.
Okay. So the next question is from Sanjay Kamar. What happens to conductivity for the case of large carrier density? I think this also is referred to the beginning of the talk.
Of large what density?
Large carrier density. So what happened to the conductivity at large carrier densities in magic angle twist feather graphene? I think that's the question.
Oh, I see. Okay, let me maybe go to that slide. Oops. Yeah, so you could ask about large carrier density within the flat band. So you could ask about, and let's go to perhaps to this. So you can see it here in this case. This is resistance versus carrier density, and this this panel ends when the flat band is fully empty, right? So this is what it does. When it reaches the fully empty limit, you get large resistance. And then as you start adding charge carriers, the resistance decreases. Then you get the superconductor somewhere here. There's a spike that corresponds to the correlated insulator. And then you get the charge neutrality and then so on and so forth. Okay. Now you could ask what happens if you dope even further into the remote bands, right? So then you start getting metallic behavior. That's it. Nothing particularly interesting happens in the remote band.
Okay, thank you. So Dennis have a question. I asked him to or her to raise his hand to talk. So I will allow you to talk now. Please ask your question.
Can you hear me?
Yeah.
Okay. At some point, you brought to us that flat dispersions of the integer quantum Hall effect have also flat Berry curvature. And I didn't mean, what do you mean by flat Berry curvature?
Oh, okay, very good. Yeah, so if you think about the integer, a single Landau level, right? So a single Landau level is an extreme case of a Chern band. Now you can ask, how do you define momentum in a Landau level to define a Chern band? Now, you may know that magnetic translations within a Landau level do not commute with each other, right? But there is a subset of magnetic translations that do commute. So these are translations, say in the X and Y direction, which are such that the corresponding unit cell encloses exactly 2 pi flux quanta, right?
Yeah.
If you exactly enclose 2 pi flux, then these two magnetic translations commute with each other. You can use these commuting magnetic translations to define a crystal momentum basis for the states within a single Landau level, right? So then from that point of view, it just becomes, we use the standard technology of an ordinary Brillouin zone, right? And then you can calculate the Berry curvature because you know the wave functions, the Landau level wave functions, and the Berry curvature is just absolutely flat. Right? It doesn't depend on this crystal momentum that you define as the eigenvalue of these commuting lattice translation operators.
Oh, perfect. Thank you.
Sure.
Okay. Our next question comes from Hank Chen. Are there any hints, experimental or otherwise, that may suggest the superconductivity at the magic angle to be topological? If so, has there been work towards its classification using, for example, Freed-Hopkins theory?
Oh, okay. It's clearly that comes from a theorist. if the question was, are there experimental, hence the superconductivity may be topological, then the answer is no. As far as I know, in all of the experiments done so far, there's nothing in them to jump up and down and say, look, this looks like it may be topological. Of course, that does not stop theorists from suggesting that some of these superconductors may be topological. There are hundreds and hundreds of theory papers on this subject. So obviously, every possible suggestion one could imagine has been made. Now, whether it's worthwhile to classify it now, I should say that in most superconducting materials, the superconductor itself can, the electronic properties, the properties of the Bogoliubov particles inside the superconductor can usually be adequately described using free fermion theory. So you don't need something heavy like Fried Hopkins or anything, which, that full machinery is needed for classification of interacting topological phases. Here, if it's a topological superconductor at all, it'll fall within the standard free fermion classification of topological superconducting phases, which has been in existence for 10 years.
Perfect, thank you. The next question comes from Pavel. Can the flux attachment picture of fractional quantum Hall effect be applied to a single valley of twisted battery graphene at a commensurate filling?
Okay, that's a very good question. And the answer is it's not clear in the following sense. There's an old problem in the quantum Hall effect, which is actually not that well understood, which relates to flux attachment. It's not that well understood even within the quantum Hall effect itself. So the standard flux attachment theories that people developed in the 80s and 90s do not pay attention to projection to the lowest Landau level, right? So you have to do something a lot more sophisticated to be able to do flux attachment while working entirely within the lowest Landau level. Okay, so for these other systems that we're not talking about, twisted bilayer graphene or ABC trilayer graphene, even when they have Chern number, if one wants to do something that's microscopically accurate and somehow blend that in with something like a flux attachment idea, then you have to solve a fairly sophisticated problem, which is not that well understood even within the quantum Hall effect. Now, the alternate is not worry about microscopics that much and just try to do something cruder, something that is more in the spirit of, a field theory type description, which throws away a lot of the microscopics. For that, you may be able to do some sort of flux attachment for these Chern bands.
Okay. The next question is, you mentioned that the flat dispersion of integer quantum Hall effect have also been a flat barrier curvature. In this sense, what does flat barrier curvature means? I guess you answered that already. So
yes,
I'll just skip this one. The next question from Jonna, could you clarify for twisted bilayer graphene, if the triality is the same around the two valleys, where did the other triality go?
Sorry, I didn't understand the question.
He's asking for twisted bilayer graphene, if the chirality is the same around the two valleys, where did the opposite chirality go?
It doesn't need to go anywhere, right? So that's what makes the band topological. Now, of course, in one valley, the two Dirac points have the same chirality. Let's say it's winding in the clockwise direction. Now, in the opposite valley, the two Dirac points have the opposite chirality, where the wave functions are winding in the counterclockwise direction. Now, of course, the beauty of the Moiré graphene is that you've disconnected the two valleys from each other electronically, right? So microscopically, both these valleys came out of the same set of electrons, but the Moire potential has disconnected these two valleys, right? Yeah, so if you wish, it went to the other valley. That's right.
Right. So when you say the chirality is the same around two valleys, it's actually the two valley from two layers, but it's on the same K point. Is that correct?
Absolutely, yeah. It's the two Dirac points within a single microscopic valley.
Right. Yes.
Right, have the same chirality, and then the other microscopic valley has two Dirac points with the opposite.
Right. Yeah. Thank you.
Yeah.
The next question: does the Mott insulator always correlate to the unconventional superconductivity?
Sorry, is the Mott insulator always what?
Correlate to the unconventional superconductivity. I guess. I'm not sure what exactly means. Probably means like if
Probably
you have
unconventional pairing symmetry.
Yeah, I'm not exactly sure what this question means. Well, if you have this question still, maybe raise your hand. We'll let you ask vocally. The next question is, should the extra Chern bands required to cancel the Chern number be thought of as extra density degree of freedom within some gauge theory?
Yeah, again, that's clearly a theorist's question, and it may be possible to develop a theoretical approach to this kind of problem by introducing a fictitious extra Chern band that at the end of the day you project out. Now exactly how that is done is not clear, at least to me.
Okay. Question from Kasra: with the HBN substrate not aligned with the twisted batter graphene sample, is the C2T symmetry at a microscopic level preserved? Would it impose the gapping out of Dirac points?
Okay, that's a wonderful question. Empirically, it does seem to be the case that in the vast majority of twisted bilayer graphene devices at low twist angle that have been studied, that empirically it seems that the C2T symmetry for samples that are not aligned with HBN, that C2T is preserved and that neutrality is Dirac-like. In fact, there were very nice experiments in 2016, which was a precursor to this modern wave of experiments done by Pablo's group, which studied twist angle of 1.8 degrees, where quite clearly you see exactly what you expect to get with Dirac points at short neutrality, exactly as you expect theoretically if C2T were present. And by now, that kind of data has been reproduced by, has been seen in many devices by many other groups at various twist angles, right? So it doesn't seem like if it's not aligned closely with the substrate, with the HBN substrate, that C2T is broken explicitly.
Okay. So maybe I'll just take the last minute to ask a question of myself. You just said the C2T basically protect the Dirac point. Like, how do I understand that intuitively? Why, if C2T is preserved, you have the Dirac point?
Okay, very good. So it has to do with the Berry phase, right? So if you have C2T symmetry, then it's easy to see. You ask how the Berry curvature transforms under C2T. And what C2T guarantees for you is that if you go around the loop, that the Berry curvature is quantized in multiples of pi. Okay, so you can either get 0 or pi or maybe 2 pi. So if you have a Dirac point, right? Suppose in some calculation you found a Dirac point. Now, your electron goes around the Dirac point in momentum space, you know that the Dirac spin rotates by 2 pi so that the Berry phase is pi. So this is the famous pi Berry phase for Dirac fermion, right? Now, so long as C2T is preserved, you can't change the pi Berry phase continuously to anything else, right? Because C2T quantizes the Berry phase to be multiples of pi. So that's what gives, so any perturbation that you add to the system so long as it preserves C to T, it will, so long as the perturbation is weak, it will preserve the Dirac points. Is that good?
Yeah. Maybe another question I had. You said the SU4 symmetry of spin and valley is broken for to see better graphene. Could you expand a little bit on that? Why it's broken?
Right. So good. So it's already broken at the single particle level because the Hamiltonian, so remember that the way time reversal acts in this system is that it takes electronic states in one valley to electronic states in the opposite valley. Okay. So within a single valley, the dispersion is not time reversal symmetric, right? Meaning epsilon k, where k lives inside the mini Brillouin zone, is not equal to epsilon minus k. Okay, both time reversal and C2 rotations take one valley to the opposite valley. Rather, epsilon k in one valley is equal to epsilon minus k in the opposite valley. Okay, so the dispersions even at the band structure level, the electron dispersion is such that at any given k point, the epsilon k of one valley is not equal to the epsilon k of the opposite valley. It's only equal to epsilon minus k of the opposite valley. Okay, so consequently, if you sit at a particular k point, you don't have SU4 rotation between the two valleys.
I see. Okay, thank you. We are past our time, so we'll stop this session and we'll continue in about 40 minutes. See you.
All right.